So let's delve into something that you guys are kind of familiar with from last week, but let's do a problem with it just to review. So speed is a scalar, velocity is a vector, as I've explained before. A great way to remember this is alliteration. S for speed, S for scalar, V for velocity, V for vector. Now remember how their definitions are different. Speed is a scalar, distance is a scalar, total distance is a scalar, sorry. Total distance is a scalar, and time elapsed is a scalar. And that gives us to d over t. Change in d over change in t. Now don't get d confused with derivatives if you're familiar with that, or don't get d confused with displacement. You can honestly notate it any way you want, but that's just the way I like to do it because it's clear in my head. You can use another common one is delta s to denote total distance, but of course some people get that confused with speed. So use whatever notation you want. Delta, don't use a, don't use v, don't use t, don't use any of the obvious ones like x, y, or z because those denote position. But feel free to be flexible with your own notation. So velocity, on the other hand, instead of total distance, is total displacement over, again, time elapsed. And this is average velocity, and I'll come to what that means, and this is average speed. So the way to write it, average velocity has this v with a bar on it, so we call it v bar. And total displacement, well, displacement is just xf minus xi. Time elapsed is just tf minus ti. F means final, I means initial, and that just gives us delta x over delta t. And this is the vector, but since it already has the bar, most people already assume that it is a vector. So as you can see, velocity is equal to delta x over delta t. But let's say we are given the average velocity. For example, let's say we're given the problem something along the lines of how far can a cyclist travel in 2.5 hours if along the straight road if her average velocity is 18 kilometers per hour. So what that means is 18 kilometers per hour is v bar. Delta x, the displacement, is what we're trying to find because we're trying to find how long she can go. And delta t we already know to be 2.5 hours. Well, this is a simple equation. To find delta x, just multiply both sides by 2.5 and you get 45 kilometers. 45 kilometers. Sorry about that. Let me just erase this a little bit. And boom. So this was just a way of showing you that if you have everything except for one piece of information, it's really easy to do it. If we said that the cyclist was 5 kilometers down the road, she reached it in a time of 2.5 hours, and her rate was 18 kilometers per hour, we could easily find the initial position that she was in. But if you drive a car, for example, for 150 kilometers along a straight road in one direction for 2 hours, the magnitude of your average velocity is what? V bar equals 150 kilometers over 2 hours, so your average velocity is 75 kilometers per hour, or 75 kph, right? But that's not really an accurate picture of what exactly you traveled at, because there could be places where you braked a little bit, maybe it's traffic hour, maybe there were places where it's open road, so you decided to have a little fun and went 120 or 130 kilometers per hour. So the sense is, it's unlikely though that you were moving at precisely exactly 75 kilometers per hour at every single instant along your 2 hour journey. To deal with the situation, we need the concept of instantaneous velocity. Now that's a calculus concept, but I'm going to try to put an algebraic twist to this. We need the concept of instantaneous velocity which is the velocity of at any instant of the time. Its magnitude is the number with units indicated by indicated by a speedometer when you're driving. So when you look at the speedometer, that's your instantaneous velocity at that moment. Doesn't tell you your average velocity or average speed. More precisely, like the textbook definition of instantaneous velocity, at any moment is defined as the average velocity during an infinitesimally short time interval. What does that mean? That means that we have, and this is a little calculus. So we start off with our definition of average velocity, and we define instantaneous velocity as the average velocity as we let delta t become smaller and smaller, extremely small. We start off with 0.1 seconds. We go to 0.0001 seconds. 10 to the negative 20 seconds. Essentially, the trend is we're making this delta t as small as possible. And so we get this notation, and I'm going to write it up here. We get that v is equal to the limit as delta t approaches 0. And we have of delta x over delta t. And we have our average velocity. And this fancy calculus notation just means that what I described here, you're trying to make delta t as small as possible. This notation means that the ratio of delta x to delta t is to be evaluated in the limit of delta t approaching 0. For instantaneous velocity, we use the symbol v rather than v bar because it's more work to write v bar than v, and we use instantaneous velocity more than average velocity. Now note that instantaneous speed always equals the magnitude, not the signage, the magnitude of instantaneous velocity. And the reason for that is because the distance and the magnitude of the displacement becomes the same when they become infinitesimally small. So when delta t is virtually 0, not exactly 0 because that would make the function undefined, but very, very infinitesimally small, like as small as you can imagine and then some. The magnitude of instantaneous speed is the same as the magnitude of instantaneous velocity. And remember, magnitude just means the number. Now, delta x, for example, the magnitude of delta x is 45 kilometers per hour. The magnitude of this average velocity is 75 kilometers per hour. If I had negative 75 kilometers per hour, the magnitudes would still be 75. The direction would be specified by that negative. Now, if an object moves in a uniform, and let me write this down here. Uniform equals constant. You're going to be hearing this a lot throughout your physics journey. If an object moves at a uniform constant velocity during a particular time interval, then its instantaneous velocity at any rate is the same as its average velocity. See, you can see here in this image that velocity of a car as a function of time in this image is at a constant velocity. And at every instant, at every single little t, no matter how small we make it, no matter how small these dashes become, no matter how small they're spaced apart, that's always going to be whatever this is, let's say 4 meters per second. But note that this isn't really realistic. It's very hard to be at exactly 4 meters per second for however long your t interval is. You're going to be experiencing a lot of forces. You're going to be changing your acceleration left and right. So this is a more accurate graph. In many situations, you don't get this. For example, a car may start from rest, speed up to 50 kilometers per hour, remain at that velocity for a time, and then slow down to 20 miles per hour in a traffic jam, then increase a little bit as the traffic jam starts to clear up. So that's the graph right here. The trip is plotted on this graph over here. So this is kind of an image relating to what I just said about this hypothetical scenario with the car. Also shown on the graph is this dashed average velocity of 40 kilometers per hour. As you can see,